particle is projected from the origin with speed u at an angle theta to the horizontal, and the only force acting on the particle is the force due to gravity. Derive the general equations of motion for the particle. Okay, so projectile motion can be modelled by splitting the motion into two components: the horizontal, i.e. in the x direction, and the vertical, i.e. in the y direction. Okay, so here we have a table with the horizontal motion equations and the vertical motion equation. We're going to look at the initial position is quite straightforward. It's 0, 0. The only force acting on the particle is gravity, so the acceleration can be written as a vector 0 minus g. Now the initial velocity will be ux, the x component will be u cos theta, and the y component will be u sin theta. Now, using this GeoGebra applet, we'll have a look at that. The GeoGebra applet I will attach to the notes of this video. So here we've got a particle, P, being launched at 45 degrees at the moment. You can actually change these using the slider here. Okay, and if we just start the motion, we can see the particle moving along like that. Okay, and then eventually reach its height and then come back. So we're going to derive equations for the maximum height, the time of flight, the range, and the general equation of this path. Okay, so we'll just reset that to begin with. Okay, we've got gravity acting downwards. Okay, so it will be minus because it's acting downwards. If we first of all look at the initial velocity, which is u cos theta, u sin theta. Okay, so basically what we've got here is that the initial velocity here, you can see there will be here, this is the horizontal component, this is the actual u here, the direction of u, 45 degrees, and we'll see that this is the vertical component. Now here, that you can get this by doing u cos theta, a little bit of trigonometry, and you see that this one here is the same as this one, so you get by doing u sin theta. So just applying a little bit of right-angled trigonometry. So, just going back to this for a minute, the initial velocity written as a vector is u cos theta over u sin theta. So u cos theta is the horizontal component and u sin theta is the vertical component. Now, if we use the equation of motion, and we can do because the acceleration is a constant, it's g, using v is equal to u plus at, then the horizontal component, there's no acceleration acting, because the acceleration is acting downwards only, vertically downwards, so it's going to be u cos theta, and then the vertical component will be u sin theta minus gt, using u plus at, so u being u sin theta minus gt. And then if we go back to this, okay, and we run this now with these actually on, okay, so the velocity, you can see the velocity here stays the same. This gets less and less because gravity is acting on it, and then it becomes lower like that. Okay, and you can play around with the app like that. So here we get to its maximum height. Now, the displacement, which is s is equal to ut plus a half at squared, then the horizontal component, this is going to be ut cos theta because there's no acceleration, so this bit here will be 0, so it'll just be u times t, which we write as ut cos theta, and the vertical component will be ut sin theta minus a half gt squared. So ut, u sin theta t, because that's what it is in the vertical component, minus a half gt squared. So these are the initial equations that we actually start with. Just to see what we mean by R, if we go back to this, okay, so this is going to be quite a long video. If if we reset the video, reset this, and we'll just take off the and just look at the displacement. Okay, at the moment you can see the displacement is 0, 0. Okay, so the displacement vector, if we start it, okay, you can see the vector r here. As we get further over, you can see it becomes a bit more visible. So let's just stop it somewhere, stop it there. Okay, so this is the displacement vector here at the moment. This is the vertical height is 19.35. Sorry, the horizontal distance is 19.35 and the vertical distance is 5. Okay, and this is represented as a displacement vector. So you can represent these as vectors as well. Okay, so let's just reset that and then turn these off for a minute. Probably the one that's the most useful to look at is going to be that one. So we'll reset it. Okay, so here, this is the initial speed that the particle leaves up. Okay, so carrying on now. So that's r. Right. So if we label these 1, 2, 3, 4, the maximum height. So the maximum height from equation 2 will occur when this velocity here is equal to 0. So if we just look at that, and if we put that there, okay, we can see, we might not be able to get exactly, okay, we can't get it exactly, but we can see here that this is very, very low. This will be virtually 0, and this will be 11.31. This one will always stay a constant. So we want to know where this is equal to 0. All right, so if we're using that, we've got to find the time where we get the maximum height. So solving that, we're going to get u sine theta is equal to gt, and therefore t is u sine theta over g. Then if we now substitute that into equation 4, this one here, we'll get the height at that moment. We know this gives us the time of the maximum height. So doing y is equal to ut sine theta minus a half gt squared, replacing the t with u sine theta over g, the time of the maximum height. This becomes u times u sine theta over g times sine theta minus a half g u sine theta over g squared. Okay, so this now becomes u times u, so it's u squared, sine times sine, sine squared over g, minus g u squared, sine squared theta over 2g squared. So the 2 comes from there, everything in here is squared. Okay, so this is u squared sine squared over g minus, now the g's will cancel out, and we're going to have u squared sine squared theta over 2g. So we need a common denominator of 2g. So that means we need to multiply top and bottom by 1. So we've got 2 lots of this minus 1 lot. So it gives me the maximum height is u squared sine squared theta over 2g. And going back to that, this gives me this distance here as the maximum height. Carrying on. Okay, same equations. Now we want the time of flight, so the time of flight t. So when the projectile hits the ground, the vertical component will be equal to 0. So looking at the diagram again, if we take that down there, here the vertical component of displacement will be equal to 0. So what we need to do is put that equal to 0. And we know we're going to get 2 places, one here and one here where the initial starting value is. Okay, so from 4, got y is equal to ut sine theta minus a half gt squared. So 0 is ut sine theta minus a half gt squared. So 0, common factor of t, u sine theta minus a half gt. So either t is equal to 0, which was the initial position that I told you about, or that u sine theta minus a half gt is equal to 0. solving that, we're going to get u sine theta is equal to half gt, and therefore t, the time of flight, will be 2u sine theta over g. All right, so that gives me the total time of the flight from start to finish. Right, the range of the projectile is the value of x when t is equal to this particular value. So what we're trying to find now for the range, we're trying to find from here to here, so we know the time at that particular point. So if we now substitute that into 3, so from 3, we're going to have that x is ut cos theta. We put t to equal to that. So 2u sine theta over g times cos theta. So it gives me 2u squared sine theta cos theta over g. Now you know that 2 sine theta cos theta, sine 2a is 2 sine a cos a. So this will become u squared sine 2 theta over g. Now if we look at that, the maximum that sine can ever be is 1, and that will happen when theta is equal to 45. So the maximum range will always occur when sine 2 theta is equal to 1, which means when theta is equal to 45. So if we go back to this, okay, if this is 45, with u being 16 and t being, well, u being 16, then the maximum range we can ever get is 26.1 when the angle is 45. If I change the angle, okay, you'll always see it will be less. Okay, it will always be less. So the maximum range occurs at 45 degrees. Okay, so that's when sine theta is equal to 90 is equal to 0. So the maximum r of the maximum will always be u squared over g, because this bit will be equal to sine 2 theta will have to be equal to 1. Right, the equation of the path. Okay, so basically what we're trying to do is what is the equation of this path if theta and u and change. Okay, so from 3, we have that x is ut cos theta, and make t the subject, so what t is equal to x over u cos theta. Substitute into equation 4, so we're going to have y is equal to u x over u cos theta sine theta. Put it into the first part of that. Minus a half g x over u cos theta. So this is actually the equation of the path with no t in it. We've eliminated t. Right, so the u's will cancel. So we're going to have, and then we know that tan is sine theta over cos theta. So we've got sine theta over cos theta. So the first part will be x tan theta minus g x squared over 2u cos squared theta. Just write that out again. Right, so x tan theta. Now we know that 1 over cos theta is 1 over cos theta is equal to sec theta. So this will become gx squared 2 over 2u times sec squared theta. And we also know from our pure maths trigonometry, sec squared theta is equal to 1 plus tan squared theta. So we'll put in here 1 plus tan squared theta. So we end up with a general equation of motion of y is equal to x tan theta minus g x squared over 2u squared times 1 plus tan squared theta. So this is actually some sort of quadratic, because we can see that this is some type of quadratic. Okay, so this GeoGebra applet I will put in the notes of the video. It does, I think, help you try to understand it. So this has been a video to show you how to derive these general equations of motion. I hope you've understood, and I thank you very much for watching.